Okay, welcome back. Today we're going to go through our Unit 5 review guide, which is all about chemical reactions. And so we'll start off with just a little bit of review for our ionic compounds. Remember that the 3 here identifies the ion charge of the transition metal. It does not mean that you have 3 iron in this chemical formula. And so because of that, we say we have iron, which is a positive 3 ion charge, cation. Nitrate, the suffix ate, lets us know that it is a polyatomic ion that is found on the back of your periodic tables. And that has a -1 charge. And in order to get these overall charges to be an overall net charge of 0, they have to even each other out. Positive has to equal the negative. In this case, doing our little crisscross method, it shows me that I need 3 of these nitrate groups for every 1 ion there. And we put the parentheses here around that polyatomic if we need more than 1, because if we don't, then this looks just like NO33 instead of actually saying that we have 3 of this entire group. All right, so just a couple of little gentle reminders there. Sodium, +1. Carbonate, another polyatomic, is a CO3 group. You can cross them, and I need 2 sodium there to balance out the charge on the carbonate. Aluminum, +3. Sulfate, another polyatomic ion. In this case, crisscross those, we see we need 2 aluminum for every 3 sulfate ions to get that charge to be 0. And then we see nickel 1 sulfate or sulfide, I'm sorry. And because it's IDE, really the only, as far as I can remember, the only IDE polyatomic ions that we provided you on the back of your periodic tables are cyanide and hydroxide. And so with IDEs, you know that more often than not, those are just going to represent the elements, the nonmetals that are by themselves. They are not part of a group. We just change their endings. So this would actually be Ni2S for nickel 1 sulfide. What are the diatomics? Honkelbrief, or whatever other phrase, Brinkelhoff, Hoberfinkel, any type of phrase that you want to remember or help you remember those. And again, diatomic means that when they exist by themselves, they do have to exist as a pair. All right. So anytime they are all alone, that is what we need to make sure we remember to incorporate, because if you do not have the diatomics when they're by themselves exist with a pair, then that's going to throw the entire equation balancing off when we get to predicting products. So just remember the diatomics. And speaking of chemical reactions, here are the 5 that we primarily go through. So synthesis, remember, has a template or a skeleton formula that looks like this. And to synthesize means to combine. So when we say a synthesis reaction, we know that we are starting with 2 elements by themselves, right? And again, I only have to give you the reactants here in order for you to identify this as a synthesis. That goes for all of our reaction types. 2 elements by themselves, they combine to form 1 compound. More often than not, that compound is going to be ionic for us. It does not have to be, of course, but again, we like to continue practicing with our ionic charge canceling out. So usually it's going to be ionic. Decomposition, that is the opposite, where the skeleton looks like that. AB is a 1 compound. So it starts with 1 compound, and then it breaks apart into we'll say multiple substances. But for simplicity's sake, more, again, kind of like the synthesis is going to result in an ionic compound more often than not. For us, the decomposition reactions are going to be more so breaking up into its individual elements that create the compound that we started with. So usually the individual elements there. So again, we'll take a look at what those look like down below. Single replacement reactions, they start with one element and a compound, and in theory, what that element by itself does is it replaces. So there's only one replacement going on here. The element most like it in our compound at the beginning. And so we say it starts with one element and one compound. And then it ends with, if it occurs, it ends with a new element by itself and a new compound, because that one element that was originally by itself took the other element's place. Again, we'll primarily be talking about single replacement reactions that involve metal elements doing the replacing, because the single replacements, we do have our activity series that we have to make sure that we remember to use to see if a reaction will occur or not. And again, the activity series that we use is from the one that we created in lab in our class, where we have magnesium, zinc, lead, hydrogen, copper, and silver. The most reactive on this list was the magnesium, and the least reactive was our silver. So in order to identify if these reactions even happen at all, we have to be able to use that activity series to say, does that element all alone, is it reactive enough to replace the thing that has already bonded? Because if in this compound that we start with here, this metal is more reactive than this one, well, then C is not gonna want to leave its partner for it, right? And so, again, being able to use the activity series there. Double replacement, again, going on the replacement theme here, we start with two compounds, and we end with two new compounds, and that's because the front metals switch, because these are always going to be ionic compounds. So we can always say two ionic compounds create two new ionic compounds. Of course, front metals or NH4, which is ammonium, that acts like a metal with a positive 1 cation charge. Those are the ones that are going to be doing the switching. So the skeleton for this was AB plus CD yields AD plus CB, because again, those front ones, they just switch spots there. So in terms of how, like, what order you write these in, of course, it does not matter. I could put CB before AD. However, within the actual compound itself, the metal or the positive ion has to be first. The negative ion has to be second. All right. And last but not least, the fun ones. The combustion. Again, the skeleton is just any hydrocarbon or any other fuel source. Sometimes it could have O in it. Sometimes you could even have N in it, but we don't really get into combustions with nitrogen. But more often than not, it'll be C, some combination of C and H plus O2 will always provide us with carbon dioxide and water. And What it starts with, of course, CH and O, right? And so you might say, whoa, well, that's a compound and an element. And for single replacement, we start with a compound and element there. Why isn't it a single replacement? Well, because of the nature of the way that these elements are going to rearrange themselves from start to finish here, because you'll notice that the oxygen ends up being a part of both of those products. So there's not just one switch that's happening where one element in the compound originally is kind of being kicked off alone. So anytime you see CHO, about 99% of the time for us, we're going to have a combustion reaction, 100%. I will even go as far as saying that. And so what does it end with? Always CO2 plus H2O. Does not matter what order you write those in again. And it also does not matter how many C's or H's you had started with, because, of course, we have the balancing that we can do in the equation. And that, of course, the easiest way to do that is to do C, then H, then O in that order, because of those O's splitting up on that side. So let's go through and balance a couple equations. In terms of balancing, you can always draw it out underneath or on a separate sheet of paper if you want. We are going to do it just kind of mathematically, where whatever coefficient we put in front, of course, we can multiply to those subscripts that we have present to then get a total of how many of those atoms are present. So in this case, I see I have 3 iron here, so I'm just going to put a 3 here, because if there's no coefficient, then we, again, understand that to be 1. We just don't write it. And so we have 3 there to get me 3 iron. I see there's oxygen here, so I'm going to put 4 oxygen on this side. 4 times 2 is going to give me 8 H's, so I'm going to end up with a 4 here as well. And then Fe3O4 can stand alone. So you can put a 1 there if you want. I will not be putting a 1 there. Just because, again, chemists are lazy, and anytime there's a 1, we don't have to really worry about it. It's understood. Down here, we're starting to get into where we have our polyatomics, right? Whenever I see more than 2 elements in a chemical compound, I end up being able to kind of package them up, even if they aren't already showing that they're packages. So anytime you see a polyatomic, if you really want to just kind of bundle it up like this, it doesn't hurt. And you can see that we need to do that anyway when we need more than one of those things. So just to show you that, what we can do is, instead of balancing nitrogen and hydrogen separate, you see hydrogen is a part of both of those. We can kind of just treat the ammonium groups as they are one thing, and then we can also treat the hydroxide groups as they're one thing, so that we don't really have to worry about all these H's flying around in different spots and trying to and potentially losing track of them. So by doing this, we can do it exactly how we balance the one above, where we just put a number in front and it multiplies not this 4 and this 1 separately, but this whole thing. So as I work through, I can see I have one ammonium group here, one NH4 bundle, and I have one NH4 bundle on the right. And then over here I have one hydroxide bundle, and I have 3 on the right there. So I'm going to put a 3 in front. And that's going to give me 3 hydroxide bundles to balance the ones I have here. And that's also going to give me 3 ammonium groups, which is going to allow me to then put a 3 in front to balance out here. And so with that happening, that will then give me 3 chlorine over here in this compound, because we're really just multiplying the number of combinations or compounds we have, or molecules, depending upon what it is, and we can then relate that back over here where we see 3 chlorine on this side. All right, so then we end up saying that if we want to, we can add 1 and 1. Those are the coefficients there. and it made our lives a little bit easier to make sure we treated those things as they were bundles, instead of doing things separate. Combustion, again, do C's, then H's, then O's. I have 3 C's on the left, so I'm going to put 3 in 1. 3 times 1 is 3 there. I need to get 8 over here. 4 times 2 is going to give me 8. And then I notice I have 6 plus the 4 oxygen from the water. That gives me a total of 10, which means that I need 10 total oxygen here. And again, put a 1 in front of the propane there, C3H8, if you would like. Down here, aluminum, there is a 2. And I like doing it this way to show you that sometimes you do need to change the coefficients. The ones that you put first aren't always set in stone. So then I see that I have 3 oxygen here, but 2 here. The only thing that those two have in common, or at least the least common multiple that they both have, is 6. So anytime I see 3 and 2 on opposite sides for the same atom, I'm going to try to get them to be 6. All right, so by putting a 2 in front of the Al2O3, that gives me 6 oxygen. By putting a 3 in front of the O2, that gives me 6 oxygen there. But that does change the number of aluminum I need. So what I'm going to do is take this, erase it. I see by putting a 2 here, that gives me 4 aluminum now. 2 times 2 is 4. All right, and then another polyatomic ion in here. But I noticed that the only thing that is off is that polyatomic. I have 2 of these groups here, whereas I only have 1 right there. So I'm going to put a 2 in front, and that's also going to give me 2 mercury atoms. So I'm going to put 2 mercury atoms there. All right, so there is our balancing section. Again, incorporate ones if you need to or want to as placeholders. You don't have to. We're going to go through some of these. Again, I'll show you how we can annotate this, but then I'm going to go kind of just through each other one as is. So for the first one, aluminum is just Al by itself. Metal means solid. The word and or combines with, we know positive or plus sign for being on the same side of the reaction. Oxygen, and we know that oxygen by itself is a part of Hankel-Briff, so it has to exist as O2, and G, or gas, is G. React to produce tells me that I have an arrow there. Solid is solid, and aluminum oxide. Aluminum is aluminum. Oxygen's oxygen. Now that they're together, it does not have to exist as O2, and now I'm going to be looking at the ion charges that they both have because they are going to be bonding together. So aluminum metal, solid by itself. Oxygen gas produces solid aluminum oxide. Now you're going to be tempted to just put a 2 here because there were 2 here. Don't, because anytime you have a new compound form, you have to take into account the ion charges that create it. And so this is actually aluminum Al2O3, and that was a solid product there. Now I balance, and this ends up being the same one as D above, just the opposite. So I have, I'll have a 4 here, a 3 here, and a 2 here. All right. Solid chunks of calcium, so that's calcium, solid, reacts with aluminum chloride solution, which is AQ. Since this is an ionic compound, I have to balance the charges. I see that this is AlCl3 to produce solid aluminum and aqueous calcium chloride. Now I have 2 new ions coming together, so I need to do a different rebalancing of the ion charges, and that is aqueous because it says aqueous there. And last but not least, now I balance the entire thing. I notice there's 3s and 2s, so I'm going to do the opposites here, which is going to provide me with those coefficients. Aqueous solution, right? Anytime you see the word solution, that tells you aqueous of lithium hydroxide, LiOH, +1, -1, those are good. Ooh. AQ. Plus aqueous solution of lead 2 nitrate. Remember, lead 2 is Pb +2. Nitrate is an NO3 group, crisscross, and it was aqueous. To produce or producing a lithium nitrate solution, LiNO3 plus 1 minus 1, solution means AQ, and lead 2 hydroxide. So we have lead plus 2, OH is a minus 1, and that is, a solid. All right, now, because we crisscross those, balance the entire equation. I need 2 in front of the lithium nitrate. I also need 2 in front of the lithium hydroxide there. Solid copper and aqueous nitric acid, I give you the formula there, react to produce aqueous copper 2, so copper 2 nitrate, crisscross, aqueous, plus nitrogen gas, or I'm sorry, nitrogen dioxide gas. So there's N with 2 O's, so there's a covalent. And then I'm going to move this over. And I'm going to add on the last one is liquid water. All right. And then to balance this one, we can do a couple of things here. One thing that I notice, again, is the coppers are fine. I see that there are 2 nitrogen here, and then there's 3 oxygen already a part of that nitrate group, so that's 6 oxygen. But then I have plus 2 oxygen, which makes 8, and then plus another oxygen makes 9. So this one's going to be kind of tough to balance, but something that I would look at is identifying what things are a part of everything and seeing if there's things that are split up. Like, I have nitrogen in both of these, so let's see if I can make a change to something on this side before I start working on adding those nitrogen up on that side. Because anything that is a part of multiple either compounds or molecules needs to be added up together if it's on the same side, kind of like the nitrogen and the oxygen on the product side there. So what I'm going to do is I'm actually going to look at the hydrogen here, because I see with the water there's 2 hydrogen and there's only 1 over here. So I'm going to start by just trying to fix that. And that's going to give me 2 hydrogen. That's going to give me 2 nitrogen. And that's also going to give me 6 oxygen there. All right. And so I'm like, okay, that works out pretty nicely. So let's keep going. And then I see, well, if I do that, then I get the 2 hydrogen, I get 2 nitrogen, but I have actually 3 nitrogen over on this side. So I'm eventually going to have to change that, which is totally okay. Because a lot of times this could be a guess and check as well. So another tip that you can do is anytime you see that you have an odd number of something on one side, it's always nice, especially if there's multiple of those elements floating around in multiple substances, make them even. Right? And the lowest number that we can use to make something even, of course, would be the number 2. So what if instead I change this to 2 waters, which would give me 2 oxygen instead of just 1, so that I can deal with even numbers instead of odd? Well, that would give me 4 hydrogen that I would need on this side. And let me do the same thing here with the NO2. What if I put a 2 in front of this so to make this nitrogen even as well? Well, that gives me 2 nitrogen there. And it also, I have to remember that I have the 2 nitrogen there. So that's actually a total of 4, which now I have 4 nitrogen on this side. All right. And then last I will check is the oxygen. I see that I have 12 oxygen here now. I have 6 there. And then I have 4, so that's 10. And then I have 2, which also gives me 12. So again, just a little trick to to try to make things a little easier on yourselves. Even numbers are a lot easier to work with than odd numbers. And the last portion of this, identify the reaction type. If single replacement, then use the activity series. I give you common ion charges for the transition metals and rebalance the ion charges. So zinc and silver are always +1 and +2. But copper and lead are the ones that I'm actually telling you what they are. So let's go on. Does this work? Single replacement. So I have to immediately go here, and then I say, oh yeah, magnesium is more reactive than copper, so it's able to kick it out. Copper's by itself. Magnesium ends up partnering up with the SO4 group. They both have the same ion charge, so that works out there. Next up, before I do that, I want to double check that that's balanced. I notice that everything is balanced, 1, 1, 1, 1. You can write them if you want. Decomposition, next one, because I'm starting with one thing, therefore it will break down into its individual parts. You may end up wanting to or be tempted to do this. That is not correct, because when those elements are by themselves, they are part of Hänkelbrief. They are diatomics, so they actually exist as partners, and that means that I need a 2 in front to make sure that the end's balanced there, and then I will put a 3 here to make sure I get the 6 hydrogen. This is going to be a double replacement reaction, which means that the front metals are going to switch spots. Doesn't matter what order, as long as the metals come first in these. So I'm just going to put the barium and the sulfate together. Barium -2 or +2, sulfate -2. Remember, if they are the same, we don't have to cross because they will cancel each other out. Plus calcium and nitrate. Calcium's a +2. This one we do have to cross, and I notice I need 2 nitrate groups there. And I look through, I end up seeing that I have the right amount of everything on both sides. Next up, only a couple more. Synthesis, because I'm starting with 2 elements by themselves, they're going to combine together. You're going to, again, want to smush them together, but cesium's actually an alkali metal, so it is a +1 ion charge. Oxygen's -2, so I actually need 2 cesium, not 2 oxygen, because oxygen, again, now is not all alone, so it does not need to be O2. And so to fix this, I just put, I could put this here, and then I noticed that I also need to put a 2 here to make this, going back to our make odds even trick. That gives me 2 oxygen there. That also now gives me 4 cesium, so I'm going to put a 4 in front of that instead. All right, a couple more here. Another single replacement. So I go up and I say, does this even happen? And we see that silver is less reactive than zinc, which means that this does not occur. So you could put single replacement and then put no reaction on a line. It's completely up to you. Because no reaction happens, that's why I put no reaction here. What would happen would have been a single replacement, so that's why you could put SR there and just put the no reaction here. Again, it doesn't matter. But again, silver is trying to kick out zinc, but it doesn't allow that to happen because zinc is more reactive, so the nitrate wants to stick with the zinc. In this case, this is another single replacement, right? A compound and an element. So I go up. Is lead more reactive? Lead is more reactive, which means this does happen. So lead kicks hydrogen out. Hydrogen is now by itself, and because so, it needs to exist as a pair. And lead is now with the fluorine. Lead's a +2. Fluorine's -1. And we get our formula there. And now we balance everything out, and I need just a 2 in front of the hydrofluoric acid, or hydrogen monofluoride for our naming rules, in order to balance everything out. Type of reaction here, this was a single replacement. That worked. G, I see CHO, immediately combustion, which means immediately CO2 plus H2O, in whichever order you prefer. Balance everything out the way that you want. C, then H, then O. I need 11 there. And then I'm going to end up seeing that By putting an 11 here, that gives me 11 oxygen, which actually balances out the 11 oxygen here. And then by putting a 12 here, it not only gave me 12 Cs, but it gave me 24 oxygen here. And so all I really have to do is worry about getting 24 more. So because there's 2 here, again, by putting a 12 here, that gives me the 12 times 2 to get 24. And if I add all of those up, that's going to end up being the same number of oxygen on both sides. Last but not least, another double replacement reaction. Beryllium and silver are going to switch places. Beryllium is going to end up with the phosphate group. Beryllium's a positive 2 ion, negative 3, 3, parentheses 2. And then silver and nitrogen are now together. So I need to rebalance those charges. And then I go to work here. I see that I need 2 PO4 groups. I also need 2 nitrogen. So I'm going to put a 2 in front of this first to try to get the same number of nitrogen. Again, it doesn't matter really where you start. And by putting a 2 here, it gives me the 2 nitrogen. It also gives me 6 silver, which means that I need a 2 in front of this one to get 6 silver there. And that's going to give me the 2 phosphate groups that I need as well. So that fixes all of our problems, and we are good to go. So I hope this helped. Again, being able to recreate the ionic compounds is a skill that has come back in this unit. So again, be comfortable with doing this, because you'll see that the vast majority of compounds that we have you either come up with from word formulas like here or predict are going to be ionic. So other than that, I hope this helped, and have a good day.